Hi everyone and welcome to another video. Today I'm going to present to you another different kind of video related to object detection, specifically identifying objects that are closer to the camera. So in computer vision we tend to use the visual sensor of a computer as a camera. The pictures that a camera captures are quite varied and can be distorted by noise and other factors. So in certain applications we're interested in determining the objects that are closer to us rather than the ones that are further apart. So what this mini project does is proposes a lightweight computer vision algorithm designed to distinguish between near and far objects by analyzing image sharpness rather than relying on deep learning models or specialized depth sensors. The underlying principle is based on the observation that objects closer to the camera are often captured with greater detail and sharper edges, while distant objects or background regions tend to appear more blurred due to perspective, focus limitations, atmospheric effects, or image processing. The first task is to load the desired image and compare its size to the size of the calibration pattern, which is the checkboard pattern we will use to split the image into smaller sections and analyze each section accordingly. So we load the image, which is this one, close far to PNG. We read that image and we check if the image was successfully loaded. If not, a message is shown. After that, assuming successful loading, the target width and target height are set here to 1920 by 1080. These are defines the resolution of the grid pattern we use, and so we have to resize the image that we load to this specific resolution as well. We retrieve the current image dimensions, we display them. So the original image size is 1920 by 1080. If the width and the height are different from what we should have, then we resize the image to 1920 by 1080 essentially, and then we output the final image size. Then we display the modified image using matplotlib. This is very easy to do, and we use matplotlib because cv2.imageshow doesn't work. It crashes Anaconda, so we just use matplotlib instead. We convert BGR from OpenCV format to RGB, create a figure, display the image, optional title, blah blah blah. This is just optional things, and this is the image that we get. So we have an image of the Gjallarhorn from Destiny 2, and this is the image that I gave it to be processed, right? Yeah, the background is slightly blurred, and the Gjallarhorn, the rocket launcher, is in focus. The algorithm then utilizes a predefined checkboard grid as a spatial or reference framework. Each input image is resized to match the dimensions of the reference grid and divided into a series of smaller analysis regions. The predefined grid is of dimensions 1920 by 1080, which is why we need to ensure that both the reference image and the pattern match dimensions so that the later scanning process can proceed accordingly. In what follows, the checkboard reference pattern is loaded and displayed alongside the previously processed image. This side-by-side visualization allows for a direct comparison between the normalized input image and the calibration pattern that will be used throughout the subsequent stages of the algorithm. The reference pattern defines the spatial grid structure used for image partitioning and local sharpness analysis. So we load the pattern, convert image to RGB for plotting, display both images side by side. So we have the processed input image, and this is the reference checkboard pattern that we'll use for detections. After that, the next step consists of extracting the checkboard grid structure through edge detection. Since the checkboard is composed of alternating black and white regions, its boundaries generate strong intensity transitions that can be identified using classical edge detection techniques. The detected edges represent the vertical and horizontal grid lines that define the analysis cells of the proposed algorithm. For visualization purposes, all detected edges are rendered in red and superimposed onto the processed input image. This overlay provides a visual verification that the checkboard structure has been correctly identified and aligned with the image before proceeding to the sharpness analysis stage. We'll calculate the cell size and display the width and height. So if I go down, the width of height and of each cell basically is 60 pixels. We create a copy of the image for drawing, draw the vertical grid lines, then draw the horizontal grid lines, and convert the images to RGB for plotting, and then just display them. And we get an image like this. This is the Gjallarhorn image I previously mentioned, but with the grid lines drawn on top. These grid lines being set from the reference checkboard pattern, right? So we now have the image basically split into smaller square sections, right? And then we can take each square and analyze it. So to do that, at this stage the algorithm begins its actual analysis. Each checkboard cell is examined independently and a Laplacian variance score is computed for that region. Cells with high sharpness values are considered candidates for close object detections because they contain a greater amount of high-frequency image information, such as edges, contours, and fine texture details. When a cell sharpness exceeds a predefined threshold, it's classified as belonging to a nearby object and is highlighted in green. This produces a visual detection map showing which regions of the image are likely to contain close objects while leaving the remaining cells unchanged. So, I'm gonna pan over the code a little bit. We need to create a detection overlay copy. Then we set the detection parameters. This is something that we'll likely need to change. Store detected cells, scan each checkboard cell. Convert to grayscale, compute Laplacian variance. I'm just panning over the code for those who are interested in seeing the actual code. And we get finally this result. Now, you notice that the detections are not perfect. You have a couple of squares that are not filled in. That's fine. It doesn't actually have a major impact on the overall algorithm. It's just kind of a little bit of annoying that these detections are not made, but we can fix that by playing around with the Laplacian threshold. So let's set it to 150. See what happens. Okay, so the detections are now a little bit better. We still have a square that's not filled in. Let's go a little bit lower. Let's go to 125. Still nothing. Let's go even lower to 110. Nope, still nothing. Okay, let's just go all the way to 100. And there we go. Now the detection is properly made, so you know that's all good. We have 152 high sharpness cells detected, and we can now take these detections and build a binary mask. So After identifying the grid cells corresponding to potential close object detections, a binary mask is generated to consolidate these detections into a unified representation. Each cell previously classified as a close object region is assigned a value of 1 white, while all remaining cells are assigned a value of 0, which is black. So we're basically turning the image to black and white. The resulting binary mask provides a compact description of spatial extent of the detected object. Once the binary mask has been constructed, edge detection is performed on the original image rather than on the extracted grid cells. This decision prevents the introduction of artificial edges caused by rectangular boundaries of the detection cells themselves. The binary mask is then applied to the resulting edge map, preserving only those edges located within the detected regions and discarding all remaining edges. So you get... Oh, I did not run this, did I? Give it a second. Yep. There we go. We have the binary mask of the close object detection, which resembles, it kind of resembles, if you look at it, the shape of the rocket launcher itself, right? But this is the binary mask that was mentioned. And then we perform edge detection restricted to only those regions marked with white within the binary mask. And what we get is this image of the rocket launcher Gjallarhorn. It's basically edge detection, but with extra steps, I know. I mean, it works, I guess. So this is how technically a computer would see it. Would see the rocket launcher as a close object. It doesn't really have any use, aside from the fact that it's just a fun experiment. And yeah, like I said, top to bottom is basically just edge detection with extra steps. But I guess it kind of works, right? It works. So yeah, I hope you enjoyed this video. Remember to leave a like, subscribe, and all that jazz. And I'll see you with Destiny videos later today or tomorrow.